Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, hello everybody. It is my pleasure to welcome Marcus Paschal and Franz Franchetti from CMU, and they're here to tell us all the wonderful things about generating parallel transforms, which they do in the Spiral project. So thank you very much.
Okay, thanks for the introduction, and thanks for having us here so that we can present our work. Very interesting discussions today. And now you're going to learn really to a greater level of detail what Spiral is all about. So first I want to say that the Spiral is used in two senses. So first, Spiral is really a large effort. It's a collection of projects involving a lot of people, as you can say, people from CMU and also a group at UIUC and at Drexel University. And the general theme in Spiral is the automatic generation and optimizations of very efficient implementations. And we have been focusing on signal processing kernels, but we also do work in other directions. And we are interested in software implementations as well as hardware implementations. And so up here you see Franz Franchetti, who is going to present the second half of the talk, and also Putya Yevgen Voronenko, who is my very talented undergraduate student who has been really very significant in developing this latest generation of Spiral, which was a lot of work over the last 2 years. So here you see the faculty involved. These are the graduate students, and then we also have a number of undergraduate students and exchange students always around, in particular in the summer. And we are funded by DARPA, NSF, and by Intel. So let's start with the problem. So here's a performance plot of the fast Fourier transform. This is the size of a Fourier transform from 2 to 4 to 2 to 16. And this is a performance plot, so higher is better. So that's mega flops. And I compare here two lines. The line on the bottom is GNU Scientific Library or numerical recipes, so they give you roughly this performance. The platform is a Pentium 4. And the best available implementations gives you the performance up here. And the important point is, first, there is a 10x difference. And second, the difference is not because these people didn't know how an FFT works. So they looked up an FFT, they implemented an FFT, the operations count is roughly the same here, same number of operations. So that means there are other things going on besides just picking some fast algorithm, fast in the sense of minimizing the number of instructions. And this is an FFT performance plot, but you could show the very same thing for pretty much any numerical problem out there, even conceivably simple ones like matrix multiplication. So what's going on here? So why is there such a large difference between a reasonable implementation implemented by some, let's say, graduated CS student and the best possible you can get? And this plot is a version of Moore's law, as you have seen probably many of those, but this particular version of Moore's law helps a little bit in understanding why it is so difficult to write fast code. So there are two lines here. So here's time, and then here is performance, and it's a log scale. So the green line shows you the increase in CPU frequency over the years, and until a year or 2 years ago, the frequency was reliably increasing, and as a consequence, software got faster and faster without you doing anything, right? If your computer is twice as fast, then any program will run twice as fast. But the theoretical peak performance of computers has actually evolved at a larger pace, and the reason is that because of shrinking feature sizes, architects can implement more functional units and more other microarchitectural features on the actual chip. So examples are, of course, a memory hierarchy and also special instruction sets. Now, you see that both lines are roughly linear, so that means exponential growth, but you see the gap is growing. And in a sense, the width of this gap characterizes how difficult it is to write fast code. Because to take advantage of all these architectural features, there is work that needs to be done, right? A program that you wrote in 1960 doesn't take advantage of a deep memory hierarchy, obviously. It will not be optimized for SIMD vector instructions either. So ideally, you would like the compiler people to take care of this by just creating better compilers so that you get all this performance without rewriting your old code. But in many cases, that's inherently impossible. And the reason is that if the performance characteristics or the microarchitecture changes too much, then it has effects not only on the code, but actually on the algorithmic level. Okay, so in a deep memory hierarchy, a completely different algorithms might be preferable, and a compiler will, at least in the next decades, probably not be able to choose another algorithm if you chose the wrong one. So that means compiler people can cover or part of this gap, but the rest of the gap is up to the programmer, who has to put a lot of effort of writing fast code. So it's now for like roughly 10 years, it's known that it's really difficult to write fast code. And if we look ahead, it gets much worse. As we all know, frequency scaling has come to an end. In fact, this arrow goes rather a little bit down. And we will probably see increases in peak performance along this line for a little longer, but through increasing parallelism. So it was difficult to write fast programs before. In the future, it will be much more difficult. So what we need is really, we need to cover this gap, we need new tools somehow. We need new tools to get very high performance without spending really a lot of time on tuning. So what are people doing currently? So there is the brute force approach, which is you take sufficiently many, sufficiently talented programmers, and you let them re-implement the same thing over and over again. That means somebody sat down and wrote a fantastic FFT, for example, for a Pentium, and then for a Pentium 2, Pentium 3, Pentium 4, a different one maybe for Itanium, and very often this code is written in assembly code. And that's actually current practice in a lot of cases. So it's clear that there are a lot of problems with this approach. It's expensive. You can only focus on the most important things, and others, you cannot tackle. And as we look forward towards the era of parallelism, this approach will become worse and worse. So there has been a number of efforts in research efforts in recent years to address this problem, and effectively creating a new area you could call automatic performance tuning. And one of the first efforts was Atlas or PhiPack, which is a generator for BLAS routine, like matrix-matrix multiplication. So what Atlas does is it generates a large set of different implementations of a matrix-matrix multiplication, different degrees of tiling, multi-level tilings, unrolling, and instruction scheduling, measures them, and essentially picks the fastest on a given platform. And then APEC is built is a library of linear algebra routines. It's built on top of BLAS, and the idea is that when new platforms come out, that the BLAS is re-implemented, ideally regenerated, and then the entire APEC library stays as it is and gets faster. There are other efforts. Bebop is sparse linear algebra. Then Flame is a very interesting project at UT Austin on automatically generating linear algebra routines, not so focused on performance optimizations at that point. There's an effort here. This is in high performance computing, a code generation effort. There's some work on adaptive sorting. Fourier transform FFTW is a very commonly used library. It's a self-adaptive library. So what FFTW does is, for small problem sizes, it uses highly optimized pieces of highly optimized modules of straight line code, and these are automatically generated, not tuned to given platforms, but generated to perform fast on any platform. For large sizes, FFTW breaks down into smaller problems. And there's a certain degrees of freedom in doing this, and FFTW searches over them to find dynamically the best way of doing an FFT for you. And then here's our own effort, Spiral, which is a program generator for linear transforms. And people do a lot of work on compiler techniques. And several of these efforts are overviewed in this recent special issue, like 1.5 years ago. So what about parallelism? Now parallelism is really the big problem, and if we look at how much these automatic performance tuning efforts have done towards parallelism, then you see that the area is still very much in the beginning. So Atlas, for example, doesn't address parallelism at all. In fact, changing Atlas to take care of vector instructions and maybe generate multi-threaded code would require a re-implementation. So it's the way Atlas is done is not scalable really to generate parallel code. In fact, it also seems that this division in abstraction levels LAPEC on top of BLAS really doesn't hold anymore, because recently talking with Jack Dongara, who's overseeing LAPEC, it seems that LAPEC is now being re-implemented to be optimized for multi-core processors. So you see that the original idea does not seem to hold to the extent that people wanted. And FFTW does support multi-threaded code, but the parallel functionality is more or less implemented by hand into the library. So Spiral is different than the other efforts in that sense, and I'm going to explain in the talk why. So here is sort of a very high-level slide that shows you what our personal take on what we believe what these efforts are trying to do, or at the very least what we are trying to do. So this is the philosophy or the idea behind Spiral. So what you see on the left side is how traditionally code is being developed. There's a high level, an algorithm level, and that's usually done by humans. That means the human learns about algorithm, the human chooses algorithm, the human might optimize algorithms in their structure and writes a C program. And then from the C program downwards, we have pretty good tools. So compilers work pretty well, and down here everything is automated. So with these new platforms in mind, and in general to get from this partial to complete automation, we need to conquer this level, the higher level for automation. So if we really want to be able to automate across all levels, then we need to do something to teach computers about algorithm knowledge. And that's essentially what Spiral is all about. It's a new type of a tool that knows algorithms, that can do all these things that traditionally humans do automatically by itself. And of course, to what extent that is really possible, that is our research, right? And we can only show what we have so far. So this is the organization of the talk. First we will give a brief overview on Spiral, and then I will pass on to Franz, who will talk about specifically about the parallelization in Spiral. We show benchmarks and conclusions. So what is Spiral? Spiral is a program generator, and it generates program directly from a problem specifications for the domain of transforms. And transforms are Fourier transforms, cosine transform, wavelets, filters. There's a large set of transforms, and some are used in all disciplines, like the Fourier transforms. Some are specifically important for signal processing. Spiral optimizes at the algorithm level and at the code level automatically, and we will see later what that really means and how it does it. And we can generate pretty much any type of code, from standard scalar code, fixed point code, vector parallel code, and even Verilog. So the goal of Spiral is really to provide a flexible program generator where you just have to push a button and you get your code. And you should get very, very fast code that is competitive with any human-written code. And the idea is that as time goes by and new things are invented, that rather than re-implementing the actual C code, we update the tool, which with much less manpower, and the tool regenerates the code for new platforms. So that is the basic idea. And of course, the real research question behind Spiral is, to what degree can we automate the implementation of numerical functionality? And the domain of transforms is a good case study, because it's actually not a trivial domain. The algorithms are quite complex. And here's an overview paper that captures our status from around 2004, and you see many people are involved from CMU, UIUC, and Drexel University. So here's a diagram that shows what Spiral is doing. Spiral is the gray box, and the user specifies the transform that he or she wants to implement, like a DFT of some size. Then Spiral works for a while and outputs a very fast implementation. So it's exactly how you would like to have it. It's completely automated. You just say what you want and you get it. And what Spiral does internally is it generates algorithms And for a given transform, there are many different algorithms. So let's say it starts by generating one out of lots of possibilities. This algorithm is represented in some mathematical high-level language. Then we perform optimizations on the mathematical descriptions, and there we perform all the optimizations where compilers are suboptimal, at least for this domain, I mean parallelization, vectorization, and so forth. The optimized algorithm is then compiled into actual C code. The C code is further optimized, then fed into a compiler. The compiler compiles to machine code. We run the code to get the performance. And the search engine looks at the actual performance and then makes a decision how to change the algorithm. So it's a feedback loop, like a human would do it, and explores different choices and then eventually outputs code. And there are two important things here in Spiral, two important principles. The first is what I said before, we have to put somehow the algorithm knowledge into the system, so we found a way of doing that here. And this enables us to generate actually algorithms. And it enables us to optimize at a high level of abstraction. Okay, and this is usually the point where very often I get here the question, so what is the input language to Spiral? And we had this question already during our discussion. So that's why I want to give a short demo, because it also shows what you can, so let's see how that works. What it really means to have a program generator. So a program generator is not a compiler in the classical sense, and it's also not a library in the classical sense. So here you see our website, and here we have an interface to our program generator. And you see here is a pop-up menu that currently has only one element, right? But now I need your imagination a little bit. So imagine here 10, 20 different platforms, right, which cover pretty much everything what you're interested in, including GPUs, including embedded platforms. You select one. And then you select the transform that you want to implement. And we can pick something. That's a sine transform of type 4. And you pick a data type, currently only double, but your imagination, think of vector code, parallel code, so we haven't put anything up here. You pick a size, and let's pick something small, let's say 6. And then optimize, here's only runtime, but we can actually optimize for accuracy as well. It's very easy in Spiral, because you just replace the performance measurement. And there's search method, compiler options, and you click. Okay, that I did not want, because that somebody had generated before, so it was retrieved from the database. So what you see here is that's a routine that runs in 23 nanoseconds, and we didn't generate it that fast. It was, okay, that is bad. So with line breaks it looks nicer. So that is essentially unrolled code. Okay, it's unrolled code. Maybe it has maybe 40 instructions. For a size that small, you want to have unrolled code. So that was not a good example. Let me try one other example. Whatever. Let's pick this one. I want to pick one that has not been generated. Okay, great. So everything has been generated already. Let's pick 5. Okay, 24. Yes, so apparently everything has been generated already. 33. Okay. I'm actually surprised that it doesn't crash. Okay. So if it has not been generated yet, then you will see essentially a progress bar that tells you how far it has been progressed, and then after a while it will finish, and you will see exactly this. So you see, this is a completely different way of presenting code than a traditional library. Right? You can generate things on the fly, and the benefit of this is that you can customize to what you really need. You can have code optimized for different platforms, optimized for different metrics, and you generate it on the fly, so it's just as good as a library, right? And you can store it if you want. And the reason why we do not generate everything we can generate and pack it into a library, because it's way too much. With the space that is spent by the current interface is not that much, but if we have everything up, including vector code and parallel, it will be quite a lot. Okay, and we have a couple of other generators actually on our website. If you're interested, you can look around a little bit there. Okay, so let's get to understand a little bit the inner workings of Spiral. So first, what is a transform? Transform is the domain that we are dealing with. Transform is mathematically matrix vector multiplication, input vector x, output vector y, and you multiply by a fixed matrix T. And the matrix T is what we call the transform. And the most famous example is the discrete Fourier transform, and the matrix looks like this. It's a dense matrix with lots of roots of unities. So if you do this by definition, it requires at the order of n square many operations, but they are fast algorithms, and they reduce it to n log n. And here's an example of a fast algorithm. This is Curie-Tukey fast Fourier transform, DFFT. And you can write it in this way. This is a DFT of size 4, a dense matrix, and because of the properties of the DFT, you can factor it into 4 factors, each of which is sparse. And instead of multiplying by this matrix, you multiply in steps by these matrices, and that actually reduces the operation counts and makes it asymptotically n log n. These are not just some sparse matrices, but they are structured. And the structure can be expressed using operators from matrix algebra like the Kronecker product. So the Kronecker product captures, in this case, actually this structure. There's a DFT of size 2, there's a DFT of size 2, and the core structure is an identity matrix. So this way we express algorithms, and we call this SPL, or signal processing language. It's just a way of writing structured sparse matrices. And there are many different transforms that are of interest in a variety of disciplines. We have currently 55 transforms in Spiral, and here's a set of 7. The DFT I showed already, that's a cosine transform. It's used in JPEG. IMDCT is used in MP3 decoding, and so forth. And I showed Curie-Tukey FFT before, and we call this a breakdown rule in Spiral. It's a divide and conquer algorithm, and every transform has a few of those. And this is Curie-Tukey FFT in the general case. So if n factors into k times n, I can write it like this. And here are a few other rules. So you see they all look quite different, but you see these operators, direct sum and Kronecker product, they occur everywhere. So with this one language, we can essentially capture an entire domain of divide and conquer algorithms using the same framework. So, and we call this rules, because with these rules you can actually generate algorithms. And in fact, we have a total of 220 rules in Spiral, and this is just the names, and they are ordered by the transforms that we have. And it was already quite some work to get these into Spiral. This represents the knowledge of roughly 40 journal papers. So we had to go through all the papers on transform algorithms, get them in the right form, and put them into Spiral. So Spiral knows pretty much the entire state of the art in transform algorithms. It's all in there as rules. So Spiral knows it, so from that point on, you don't need to look at the papers anymore, ideally. And Curie-Tukey FFT is just one of those. So now here's how we go from the problem specification down to the actual code. And these are the steps. So given a transform, Spiral breaks it down using by selecting rules, and there are choices, and conceptually by making decisions on which choice to choose, you get conceptually a tree. We call this a rule tree. Okay? So it's just a divide and conquer strategy. By plugging in the actual rules, you can translate this into, we translate this into an actual formula that looks like this. It's just a sparse a product of sparse structured matrices. Then we translate this mathematical expression into another one we call sigma SPL, which I'm not going to talk about in this talk. But this is another abstraction level we need actually to perform certain optimizations on loops. And then this is translated into C code. So you see this is an automated design flow going from a transform down to the code. And what is important is really the different abstraction levels, because each of these abstraction levels serves a purpose in Spiral. So up here is just a problem specification. The tree representation we use for simple manipulation. Remember, there's a feedback loop and a search. So if you have a breakdown strategy and now you want to consider a different one, then that's very easy to do on the tree level. You just change maybe a subtree expansion. Also, tree lend themselves to dynamic programming, which is an optimization strategy that we use. Then when we have, and in fact, by searching over the different breakdown strategies, we effectively optimize for the memory hierarchy. And that's heuristic because we do a search. The rest is not heuristic. At the formula level, we optimize for parallel platforms like vector instructions and shared memory platforms. And what we do here is we take formulas and transform them into different formulas that are better. So all the parallel optimizations go on here. At this level, sigma SPL, we do loop optimizations that are not done by compilers on the C code level. And then finally, on the C code, we do some standard optimizations that compilers should do but often do not do. And these are simple things like constant propagation, constant folding, and algebraic simplifications. So that's really important in Spiral. So our philosophy is do the optimizations at the right level of abstraction. And the right level means is that's at this level it's A, possible, and B, it's you can do it efficiently. Okay, so going from a formula to actual code is quite simple because these structured matrix expressions, you can actually visualize them and it becomes pretty clear how to translate them into code. And this is a simplified example how one could translate SPL constructs into MATLAB-style code. And this is an important example for this talk. It will occur several times. It's the tensor product, identity tensor a matrix, and that's just repeating this matrix like this. So you see, when you apply this to an input vector, you see this has a great structure, right? You can loop it, you could do it in parallel, which is what we're going to do later. You could do lots of different things with it. So it's actually very easy to understand that this can be just implemented as a loop that applies A to consecutive segments of the input vector. Okay, so getting correct code is really easy. Going from a formula to correct code is really easy, right? You could implement this in 2-3 days. But getting really fast code is very difficult. And it's so difficult that I have to hand over now to Russ.
Okay, thank you, Marcus. So I'm going to talk about the little bit more formal part here about the parallelization in Spiral, and I will show a little more formulas than Marcus already did. But let's start with a little observation here first. So we are targeting a couple of different types of parallelisms here, and in a traditional design flow, down here would see the compiler, and that compiler would then try to extract this parallelism. And what we are doing is we move that parallelism extraction all the way up to the algorithm optimization level. So we move it up to a higher level of abstraction and try to gain by that. And so the idea in Spiral is we have one methodology to deal with all these types of parallelisms in the same way with the same framework. And now let's take a look at shared memory as a leading example here. So the first thing when we look at the example that Marcus showed us before is we have this tensor product of identity matrix and A, and well, it's a block diagonal matrix. That means if we have 4 blocks, the red, the yellow, the blue, and the green one, we can assign each block to a processor because everything is completely independent. You could parallelize everything nicely, and it's really p-way, embarrassingly parallel. And if all the A's are the same, that's why it's also load balanced. So that's really nice. So that's really the good guy for shared memory. Now, there are also bad guys. And one example here is that stripe permutation that permutes the data according to this graph. And again, let's start out with the red and the blue processor. And now let's take the data vector and divide it into cache lines. And now you see the red cache line is held by the red processor, and the blue cache line is held by the blue processor. And by writing in that permutation, on the right side, you see that in the same cache line, there is a red and a blue element. And that means that here false sharing occurs and the cache becomes a problem. And that's one of the things you really want to avoid here. Now the task is we need to find a way to rewrite formulas so that we get these guys but don't get these guys. That's really the idea here. So basically we need to extract these tensor products, and we need to make sure to keep cache lines as an atomic unit here. So the question is, how are we going to do that? Now we have 3 steps, and the first step is we look at the architecture and we model it in a very high level of abstraction. So we extract crucial hardware parameters, and there's one which is the number of processors P in the system, and the other crucial parameter is the size of the cache line, which we denote by mu. And now what we do is we introduce into the SPL language tags which contain this information. So we have here a formula A, and we tag it with the SMP P, mu tag, which means we want this formula to be implemented on a shared memory machine with P processors and that cache line size. Now, what that really means is that within our framework, the tags express hardware constraints within our rewriting system. So that's the step one, model the hardware and express it in tags. The next step is to identify the good guys. And what we want to have is, we want to have load balancing and we want to avoid false sharing. So if we go through the library of the basic formula constructs that we know of, then we see that that one we already know. That one is a generalization of that one, where the matrices in the block diagonal are slightly different. And that here is basically a permutation matrix that only permutes full cache lines. So there is nothing happening inside a cache line, but only cache lines are shuffled around. So these are all nice. And whenever we find one of those, we can tag the operator to tell the system, well, we're done. So that means really that is already nicely parallelized. Now, starting from these constructs, we can define a formula as fully optimized for shared memory if it contains only these objects, products of these objects, or tensor products of this form. So then we can formally prove that formula will work well on a shared memory machine. Now the next step is we need to identify how to extract these good constructs and how to take formulas that are not in the right shape and move them into the right shape. And yeah, these are a couple of such formula rewriting rules that we have in our system. And yeah, so what happens is the tags get propagated, the formulas we use some mathematical identities from matrix algebra to express these or derive these rules. And important thing is there may be choices, and you may in the rewriting process need to do things like backtracking to find a solution. So that's how the whole rewriting system looks like. And now let's take a look at one of these rules to see what these actually mean. For example, you want to rewrite A tensor In for P and mu. What you as a programmer would do when you look at the code that one describes is you would like to tile the loops and schedule the loops in a certain way to make sure that different loop iterations that touch the same cache line stay on the same processor. That insight is expressed by this rewriting rule, and that leads finally to that code that has this property. And what we now had to do is basically to look at different constructs and think, how would you like to do it? What's the basic idea here? And then express it in these rules. Now, we have an example how the whole system works in practice. We start out with a DFT of a size m times n and tag it with s and p, p, and mu. Now, the rewriting system picks the Cooley-Tukey algorithm that Marcus showed before. Then it starts propagating the tags around. Then it starts applying the rules that we've seen before. And right at that point, it stops because it's done. And now that formula looks a little bit messy, but by going through it and comparing it to the definition that I showed before, one can see that that formula indeed is fully parallelized and nice. So the blue ones are all IP tensor something. That means they work well on P-way parallel machine. And the red ones are also tensor I mu, which leave cache lines intact. So that algorithm here is a good algorithm for shared memory machines. Now, we have applied that to shared memory, and let's summarize what we've done here. We do the parallelization at the mathematical level, and we use rewriting. And what we get is we get a space of reasonable algorithms, and within that space of reasonable algorithms, we can search to find the really good ones that also work well for the memory hierarchy, for example. And we don't need any compiler analysis here, because everything works with rewriting and pattern matching, so it's much cheaper. And it's a principled but domain-specific approach. And the nice thing is that you can apply that same idea now to other types of parallelisms. For example, we can go after short vector SIMD extensions like Intel's SSE. Now, what is SSE? Just a short reminder. We have here an extension of the instruction set architecture, and that thing can do multiple operations at one time, and multiple values are packed together in vector registers. So that's a picture of a four-way vector operation. We get vector registers here, we get vector operations here, and there are really many different vector architectures out there, and we want to deal with all of those. And there are a couple of problems why it's hard to use these, like the compiler problems and low-level issues and so forth. The real important message is that if you're going to use SSE, and you do it in the wrong way, you can easily slow down your program by just throwing in SIMD instructions. And that's what we don't want to do. So what's the basic idea to vectorize for SIMD? Here we have a data flow graph, and it's A tensor I mu, so the identity matrix is on the other side this time. And the characteristics here is that we have block operation and the tensor product preserves alignment. And if we now take this I new and look at it as an iteration, you see that it iterates over the data like that. That means the data access things in a stride, and after that happened, a clear way to vectorize that thing is to replace that iteration by a four-way vector operation. So that's the basic insight. That thing here can be vectorized right away. Now there is again a problematic construct, which is again a stride permutation. And here the problem is if you have a red register and a gray register, and you want to permute the data that way, then data has to cross register boundary, and you need to figure out how to do that, and you need to know the right shuffle instructions for that. And the task here is to find rewriting rules to extract the tensor product, that's the good one, and to minimize such in-register permutations. That's the goal here. And now what we're trying to do is to design a rewriting system that does that for us. So we again have our three-step procedure as in the shared memory case. The first thing is we identify the crucial hardware parameters. What we have here is the vector length. That's the important thing about the SIMD vectorization. Next thing is we need to identify the good formulas that map well. Well, we have already the A tensor I new. That's a little bit broken here. And then we have a couple of base cases that we can derive from the vector instructions that the architecture supports. And we just need to build these permutations somehow, and we do that automatically. And we again can define what does it mean that a formula is fully vectorized in the same sense as we did it for the shared memory machine. Well, and the third step is, again, we need to identify rewriting rules. For example, we have I tensor A here with vec. It turns this tensor product around and propagates the tags around and so forth. So that's, again, the same three steps for shared memory we now did for vectorization. And here we have one of these base cases that's specific to the SSE extension sitting around in the formula. Now we are again back to our example of vectorizing a DFT. We start out again with a DFT of Mn. This time we tag it for the vectorization of a new way. We again expand the formula with the Kulityuki algorithm, rewrite, propagate tags, and so forth. And that's what we get this time. And now if we start inspecting that formula, we can prove again that it's vectorized perfectly in the sense of our definition. The blue ones are all these tensor products that we figured out that are the good ones. And the red ones are base cases which we know how to deal with. So that formula is fine. So formula is vectorized with respect to our definition. Okay, so we had now shared memory, we had now SIMD vectorization. Next thing we can look at, and I will just do that a little bit more quickly, is message passing. Here the governing idea is, okay, you have IP tensor A. That means there is no communication between the processors going on. That's what you need to know. And then we have explicit communication. Whenever you have a permutation of that shape, you can basically write a little MPI program that does the explicit communication here. So we know again some constructs, and what we need to do is we follow the same three-step approach as before. We identify the hardware parameters, in that case P-way parallelism. We identify the good formulas like that, and communication. And we identify rewriting rules that break down formulas into only good ones. And now if we did that, we get the same thing again. We get a DFT parallelized for MPI for P processors. And it starts out the same way, but here it comes with a little twist, because what we wanted to do here is that we start out on P processors, but for some reason we want to scale down to only Q, which is smaller than P processors in the middle, for certain reasons. Okay, and what we see here is the whole formula starts out with data distribution on P processors, but here in the middle it rescales from P to Q, and here from Q to P back. So you can even do such rescaling within that framework. And that thing, again, is optimal with respect to the definition of parallelization. So now we had shared memory, vectorization, and MPI parallelism. So what's coming next? Next we look at the graphics processor. So how do we compute on that? We use pixel shaders. And how would we characterize the pixel shader? Well, it's massively parallel SIMD units. The shader programs have to be kernels that are written inside a for all pixels do loop. And we have some interesting memory features, which is textures and frame buffers, and the memory is rectangular in nature. Now, the tag that we get is GPU TC, where T means how many multi-target rendering, describes the multi-target rendering capability of the hardware. So a pixel shader can produce T pixels at the same time, provided they go to different targets. And it computes pixels of which are C wave vectors, where C typically is 4 for red, green, blue, and alpha. Okay, and now we throw on our complete system again, and what we get is that formula here. We start out with a DFT R to the K with the tag, propagate it around, and end up with that formula. Now we start inspecting what does this formula actually mean for us. Now, we start out with the green ones. The green ones are the kernels that become the pixel shader programs. The blue ones describe the fact that we have to do 4 old pixel do loops. Then we have C-way vectorization. Because we deal with complex arithmetic, we only need 2-way vectorization here. So the red blocks describe the fact that we operate only on complete and full pixels. And then we have the brown guy here and here. And these brown things describe the fact that it's multi-target rendering. Each pixel per kernel must go to a different target texture. And same thing again, we can define what does it mean a thing is fully parallelized for a GPU, and we can prove that that works. Now, we can do the same thing for streaming computation on FPGAs. That here you start out with the DFT and stream, and that's the formula you get. And you see that the data comes in at R to the S words per cycle, streamed through. And similar to the vector case, we have again base cases that need to be built in a specific way. So once you go to a thing like the IBM cell processor, you need to do multiple of these parallelization techniques at the same time, because the cell processor comes with SIMD vector unit, then multi-threaded core, then message passing through DMA for 8-way SMP multi-core, and then there is some memory streaming also involved. So you really have to build together all these different technologies to make use of the cell processor. And we are right now in the process of getting Spiral to generate code for the cell, which is generate streaming, message passing, and vector code at the same time. So here it gets really complicated then. Now, all that was very nice, and we've seen the formulas all look wonderful, but the question is, how does it perform in practice, in real benchmarks? So the first benchmark that we're looking at here is we look at generated multi-core code. So we always have the same way of benchmarking. The x-axis is the problem size, so that's 2 to the 6 up to 2 to the 20, FFT size, data points. The y-axis is megaflops per second, which is a performance measure, and higher means better. And we compare against FFTW3, the software package that Marcus introduced before. So, and when we look at that graph, what we see is, first, we take just a sequential FFTW and sequential spiral codes, the thin red and black line. And sequential FFTW and sequential spiral code is almost on top of each other, so they are approximately the same performance number here. So that means we start out from a relatively good baseline, or from a good baseline. Now, next thing is we turn on the SMP capability of FFTW, and you see you get that black line here. That's how FFTW can parallelize on that multi-core chip. Then we start parallelizing Spiral, and we get that red line here. That's automatically generated Spiral multi-core code. So you see that Spiral can parallelize much earlier than FFTW. We get here about a factor of 3 speed up for 4 processes, and that's a Opteron dual-core cluster, dual-core, 2 times dual-core machine. We get a factor of 3 out of 4 processes. And what you see is the performance drop here. That's when the problem gets too large for level 2 cache. So once you get out of cache for FFTs, the performance always drops. But the speed up we can maintain here. So the next thing that's interesting is if we look at how many processes are used by Spiral and FFTW. We see that Spiral starts using 2 processes at 2 to the 9, while FFTW needs problem size 2 to the 12 for that. And we switch to 4 processes right away, while FFTW has so much overhead from parallelization so that it makes sense to go to 4 processes only at 2 to the 20. So what I want to say is that here the problem size is resident in the level 1 cache of a single processor, and it runs for about 10,000 cycles only, and still we can get parallelization speed up. That shows that Spiral can really make use of the new multi-cores, where the communication-computation balance has shifted a little bit. FFTW is just a SMP parallelization, and because of that, it cannot take advantage of the specifics of the new multi-cores. It really pays off to use the multi-cores in the right way, but one has to do something about it. So next benchmark is the SSE vectorization. We again start out with the scalar spiral code that again is on par with FFTW on that machine. We are now on a Pentium 4 and we do 4-way SSE float. And the red line is the automatically generated spiral vector code. And what we see is that Spiral gets about a factor of 3.5 plus speed up from 4-way SIMD, SSE. Now, the next idea is we take the Intel compiler and turn on the vectorization flag, so we let the compiler vectorize. And what you see is that the Intel compiler can get about a factor of 2 speed up, but it can get nowhere near to where we can get by generating explicit SSE code. Next thing we want to do is, of course, we want to compare against the MKL and FFTW SSE version. And if we do that, we see that our code performs comparable to expertly tuned, hand-tuned code and to FFTW. And this MKL, the blue line, is most likely hand-coded assembly code. And FFTW is vectorized, but it's not automatically vectorized in the sense we're talking about automatization here. Okay. Now, if we switch away from 2 powers of 4-way to 8-way, what suddenly happens is that we're much faster than the Intel IPP, because it's much harder to vectorize for 8-way vectors as for 4-way vectors. And so what we can see here is that for some problem sizes we are comparable, for others we are just much faster. And the nice thing here is that we can show that automatically generated code is really fast and faster as hand-tuned code, which is not a usual thing to say for automatic tools. Okay, next thing to look at is what about our MPI code? And what you can see here is that MPI code also outperforms FFTW 215 in that case, in that specific setting. And that rescaling that I was talking about, going from P to Q processors in the middle, pays off for the problem sizes 13, 14, and 15. So it really is a good idea to have that available if you need. So, oops, something bad happened here. Okay, so the next benchmark here is GPU versus CPU. We're here on a Pentium 4 plus a NVIDIA 7900 GTX, and we are looking at a Walsh-Hadamard transform, which is similar in data flow to the FFT but has less operations. And what you can see is that while we are in cache of the CPU maintains a performance of about 4 gigaflop. And then once it goes out of cache, it rapidly drops down to a plateau of 1500. And the nice thing is that the GPU really starts getting fast around that problem sizes, and then really goes up to 5000 and comes down to 4000. So if you take the envelope and take the maximum of both, you can see it really pays off to combine GPU and CPU and pick the right one for the right problem size. There is really a potential here. And now we have one more nice benchmark here. That's the cell processor. We do not have access to a real cell machine, but nevertheless we use a simulator to port to the cell. And here we just port to the vector instructions of a single SPE, and we show what the simulator tells us about the speed up by doing so. But the real point here is that we can use a simulator to port the whole system, and once the system becomes available, we just rerun the optimization and we're done. So we don't really need the performance characteristics to port. We only need to have one final run to make everything fine. So now let me conclude here. So that we presented here a completely automatic generation framework for fast numerical kernels. We show that it's really possible to automatically generate such kernels that are competitive or even faster to handwritten assembly code. And the key here is that we have a high-level language and approach to algorithm generation and algorithm optimization. That's a thing that usually is left to humans, and we incorporate that in our system into the computers. And the nice thing is that the same approach and infrastructure can be used, or we are using it for loop optimization, different forms of parallelism, software, and even generation of hardware. So, and just a little reminder about our philosophy up here. So thank you very much, and I'm ready for questions, and maybe Marcus is joining me.
So one thing, you flash up all these formulas, and I'll be honest, I had a little trouble following some of these formulas in real time on a slide deck. How it seemed to me that what you were doing is you were looking at the target architecture and picking out some primitives that would be efficient, and then trying to target those primitives. Is that a correct understanding at highest level of what you're doing?
So what you basically do is you start out on the top with the algorithm, then you model the bottom, the architecture, by finding these primitives, and then you run a kind of a backtracking search to map the algorithm to that basic blocks.
Okay.
So the primitives are formula constructs. So there's no primitive that is implemented by hand. So that's very important. In all this, there's no piece of transform code that is written by hand. Nothing. It's all generated. That's very important. So the primitives are which formula constructs give you exactly the structure that you want. And if you work with formulas, a little bit, then it's very easy to identify them. So you want p-way parallel computation, for example. And then what you want to do is you want to take formulas and manipulate them so that they consist exclusively of these nicely structured primitives.
Yeah.
Have you thought at all about any other problem domains that might be suitable to this same approach? I mean, there are some nice properties of FFTs that let you do these things, of transforms that let you do these things. What other problem domains are there that might be, suitable for this kind of approach?
Yeah, so we're right now in the process of looking at different domains that we want to apply this approach to, and it seems, for example, for Viterbi decoding and for some linear algebra problems, we already know how we could do it. One important thing is it cannot be data dependent. That's one of the major restrictions for these algorithms here.
So at least at this point, we have not looked at data-dependent things. So the next natural step is essentially, as Franz said, Viterbi, some linear algebra, and there's some other numerical kernels where we believe we can actually generalize exactly this framework so that it encapsulates this larger class and has transforms as one specific instance. Also in this presentation, we always use the DFT as an example because, of course, the most important, but there are, as you've seen in the beginning, there are lots of other transforms, and quite a number of them can be handled with exactly the same framework.
Also, when you generate the SSC instructions, you're using compiler intrinsics?
Yes. So we use SSE, also Altivec, and for the IBM Blue Gene machine, MMX, and so forth. So we have used a couple of these, but the important thing is there must be compiler intrinsics, otherwise we're not going to do it.
So when we go back to the GPU one, did you guys actually have time to look into why, for small problem sizes, the performance was poor?
It's the
performance
thing.
was,
Yeah.
wasn't just poor, it was truly awful.
Yeah, there is some constant overhead, and we're using CG, and so there seems to be some constant overhead that just makes it absolutely unusable for small sizes. We didn't look into detail into the problem, but that ramp up is clearly a constant.
Isn't it the load and store phase?
No, it must be something from maybe compiler just in time, something. I'm not sure what really happens there and what how is using to exactly do that. There is some constant thing going on there.
So fact is that one DFT library that we found, which is sort of a benchmark for us, their performance curve exhibits also the same behavior. So still we need to understand this a little bit better, but we are probably not the only ones seeing that.
One of the things we work on in Accelerator is breaking things up on the GPU into the largest possible pixel shaders to try to amortize the startup overhead. There's some overhead associated with every pixel shader that you start and you execute. So that's one of the things we do in Accelerator. So it doesn't quite seem to fit into your formula-driven model. I'm not sure what it fits into, other than an observation that
Well,
it's almost like we want your formulas would be translated down to pixel shader code, and we really want the longest possible formula that isn't actually broken up into separate. Anyway, we should probably talk about this after you finish your talk. So, yeah, so this is very interesting.
One other question on the input. You seem to have a menu of a set of transforms that you recognize and handle and,
Right.
and input sizes. Do you allow combinations of them? Let's say I wanted to do a sequence followed by, do you allow it?
right, yeah.
Are
So not in the web interface, but in the underlying system, we can express combinations of that. For example, a convolution gets broken down into a DFT, diagonal, inverse DFT. And just things like that you can express. But we did not put that into the web interface.
Okay.
Okay. Thank you.
Thank you very much.
Thank you very much.